Next up, we're bringing in Ben Bao, who is joining us virtually via Zoom. Ben is a software engineer at Meta, and he is the tech lead on torch.compile. And tonight, he's giving us a sneak preview into new work on running PyTorch inference without Python.
So, hi everyone. I'm Ben Bao from PyTorch compiler team at Meta. So it's my pleasure to share some of our recent work with the audience in this workshop. So the title is like from PyTorch models to standalone binaries, right? Let me explain a little bit by starting with this question, like how fast can you deploy a PyTorch model? So the context, I think probably we need more context and get aligned on what I really mean by this. So let's suppose you have a computer, right, that has, NVIDIA GPU, and you already have the operating system, let's say Linux, and also CUDA library installed on your computer. Then what is the faster way to get a PyTorch model running, right? We all know like PyTorch is, your model is written in Python. So, which means you probably need to download and install some virtual environment. And also after that, you have to install Python, you have to install PyTorch, and maybe some other third-party libraries. And then somewhere you find these model files in Python. And then obviously you also need model. And model is like the core of your brain, right? Like those are usually large, but inevitable, you have to download them. So if you look at this flow, right, like, well, let's think about like, what if I say, hey, you don't really need this to download the workflow? Like, we don't use Python, right? So which means you don't need to download that, you install that. You don't need to download and install these. And instead of giving you model files, let's say I give you a model a single binary that with a binary, you just run it like with. Of course, you still have to download your weight. And then by doing that, you basically can achieve a pretty fast way of quickly get a PyTorch model up and running. Okay? So obviously, with this approach, there will be minimal dependency. Like you don't even need to install libtorch, which is a C++ library for PyTorch. And then you will get a very small binary size, right? I shared a screenshot here. Like in my local experiment I have done is I have turned a Llama 3.1 model. Like if you look at first line of the files, it's basically the binary is 8 megabyte, and that's it. And for the weights, it's 8B and with BF16, so it's going to be 16 gigabyte weight. That's still, as I said, that still will have to be used, right? Yeah, so basically, this will be like kind of a minimum, the quickest way you can get your PyTorch model running. So, what's behind this magic? How can we actually achieve that? So the magic really boils down to this like ahead of time compilation flow in PyTorch 2. I'm not sure how familiar the audience is with PyTorch 2 compiler stack, but for the regular PyTorch 2 stack, then what you have is we call the compilation, right, which is basically the upper part of this graph. For this flow, then we have something called Torch Dynamo as a kind of like a front end to your compiler. That's a way to capture a graph from your model code. And then that model code is fed into something called torch inductor. Also, I can call it JIT inductor here. And that will kind of optimize your program and turn them into Python kernels, which will be further lowered to run on your GPU. And for our non-kernels part, there we also will generate Python code as Python wrapper code, kind of managing the kernels and managing data. I will have some simple example show what I mean here. But essentially, like the upper half is how the regular PyTorch 2 compile flow looks like. If you use torch.compile in your code, that is what's happening under the hood. Right? The lower half really shows like instead of doing that, we actually can do ahead of time compilation. Right. So now with the front end, we use torch compile. That is a ahead of time way to export your program into a single graph. And that graph will be fed into a special mode of inductor, torch inductor, which is called AOT inductor. That will, again, it will generate Trident kernels, but then it will further compile that down to Cubian files, which is like the kernel binaries for NVIDIA GPUs. And for the wrapper code, we will generate a C++ code instead. And then, these with plus weights and some like metadata information will be packaged into a .pt2 file. And we have utilities to actually run this in the native world. But let me show this very simple example. Give you a rough idea like how that AOT compile looks like. And suppose you have this very simple model, right? Like, it has this optimization forward function, and it calls sine operation first, and then multiple. Then there's a cosine operation. Right? So that's the Python code, PyTorch code. Then after you run the torch compile, right? Like if you run torch compile, I highly recommend you use this like torch_logs equals to output code to see what actually our compiler generates for your both the kernel code and wrapper code. And in this case, let's say for the first line operation, we will generate Trident kernel for this. And roughly it looks like this. And then if you look at the generated Python code, right? So I have highlighted a few like functionality here like, to tell you what our wrapper will do. For example, it will take care of things like setting the string, CUDA string. It will allocate intermediate tensor, like here in the empty string, and then it will invoke this Python sine function, like kernel you just saw. But then in some other cases, it doesn't always generate Trident kernels. Sometimes it will just call back to what PyTorch eager implements. So we call it fallback call. For example, here it calls external kernels mn, which calls the PyTorch implemented multiple. Then also you can do things like reuse your buffer for memory. So these are in Triton. If you do the ahead of time compilation, this is in Python. So if you want to do ahead of time compilation, then you cannot do this, right? You just have to do the equivalent for CPP code. So I will quickly go through this. But then, once you get the C++ world, mostly you have one-to-one mapping with those functionality I just mentioned. For example, you have stream setup, you have empty threaded, and you launch a CUDA kernel for the equivalent like Trident kernel generated Cubian files, and then you have ways to call back to fallback blobs. Again, you can still do the memory management by moving buffers, moving tensors around, right? So this AOT inductor thing is not something like completely new. We started like 2 years ago, and it gets pretty like mature over the years. So one thing we did there is we defined a clear small subset, interface surface that interacts with libtorch. But for example, like if you see like entity strategy here, instead of calling like libtorch version of empty strategy directly through C++, we have provided an isolated C interface to do that for you, so that we can get a stable ABI when we talk about the keep the ABI compatibility for the old models you compiled in the past. Right? Because we were able to do this, we have a small clear defined C interface. So what you can imagine is, what if, let's say, I provide a smaller, slimmer library than libtorch that just implements this basic functionalities. All right, then suddenly your generated LTI generated code doesn't have to use like libtorch for your model to run. Right, this is really what makes this like the previous kind of example I showed you, the Llama 3.1 example I showed you, like how you can boil down to like 8 megabytes to get it run. And this is my last slide. This thing is still being actively worked on, and it will come soon. But yeah, just to try to give you a quick idea on this, like new thing we're kind of excited about.